Thank you very much, Detlef, for putting together this wonderful program. Yes, I hope to give a talk which will give rise to discussion. So the title is not my one. I found this in the program. So I should talk about whether a physical theory needs an interpretation. And if you ask a philosopher of science what an interpretation of a theory is, the usual answer you get that is to interpret a theory is to answer the question of what the theory tells us about the world, assuming that it is true, approximately true. And approximately true means, in this case, that it contains elements of which we have reason to believe that they put a constraint on any future theory of the field. So, for instance, Bell's theorem can be seen, or we have reason to believe that Bell's theorem puts a constraint on any future theory, whatever that theory of the quantum domain will be like. So, interpreting a theory means spelling out the ontological commitments of the theory, and that usually is what is called metaphysics, what comes after the physics. And the claim, the first claim I will make is it is an illusion to think that you can read your metaphysics off from the formalism of a physical theory. So there is no neo-positivist way of simply deducing metaphysics from physics. This is sometimes called naturalized metaphysics, and of course you should naturalize metaphysics in the sense that you should talk about things physics talks also about and not about other things, but the method cannot be the one of simply reading your metaphysics off from the physics. And you definitely don't need an interpretation of a physical theory in the sense that whenever you have a queer fish, whenever there's something queer in your formalism, you put a metaphysical sauce on it so that it should smell well. So this is just not coming after in the sense that you put something on top of the formalism to be quiet or so. There was some bore, etc. Someone said you cannot ask certain questions. Said, so something like this would be bad metaphysics. And I'll have a few examples in a minute. You need an interpretation in the sense of what was called in the old days natural philosophy. So Descartes or Newton considered himself as a philosopher as well. And within Newton you cannot separate the physics from the metaphysics. It's one package. You put a certain metaphysics into your physics, and the physics in turn shapes the metaphysics, tells you what the metaphysics can look like, but you have to put some metaphysics into it first, so you get a certain package which involves philosophy or metaphysics and physics together. And what I will do is I want to give you two examples of such packages taking up the topics discussed before by David Albert and Tim Maudlin. But to warm up, just to give you, here's a list of examples of unfounded metaphysics. So some people claim that quantum theory tells us that the ontology of physics involves observers or measurements associated with Copenhagen. And well, at the conference about quantum theory without observers, we don't have to talk about that. The main problem there is that those people who say this, they never offer a definition or any clear description or characterization of what an observer or measurement should be. Some people say that quantum theory forces us to change. We can have discussion afterwards. This is just to warm up, so it worked. You're the first. Jörg Fröhlich is the first to contradict it. Okay, so the second claim. Someone will contradict me, hopefully. Quantum theory forces us to change logical laws. Quantum logic. Why is this wrong? Because it presupposes a naive realism about operators, as if you could read your ontology off from operators, or as if operators don't commute, this would tell us something about truth conditions, ontology, or logical laws. Of course, it does not. Quite widespread claim, I don't have put in anyone here, not to offend anyone in particular, that quantum theory tells us that probabilities are part and parcel of the ontology of physics, in contrast to probabilities in classical physics. Well, what's wrong with that? That even if you have a probabilistic law, a stochastic law, such as in the GRW theory, the standard philosophical views of probabilities still are applicable. Frequentism on the one hand, propensities on the other hand, just to name a few. And the fact that the physics or that the probabilities end on such a law does not determine the philosophy of these probabilities. Quite other claim, move on to two now very strange things. So some people thought that quantum theory vindicates free will. So I located this in Pascal Jordan, but it has recently made some reappearance in the literature by the so-called free will theorem of Conway and Cochin. And the only thing I can say to that is that these people should, well, look up in the Stanford Encyclopedia of Philosophy or on anything about what free will is and what the conception of free will could be. So what everything is in there is a complete naive conception of free will, and I find it scandalous that such things are published as being about free will, so that not an editor or someone tells, well, stop, please look in a philosophical book, first of all. Other strange claim is that classical physics tells us about what there actually is, and quantum theory is suggested or is supposed to propose an ontology of possibilities, and the actualization of these possibilities then involves time in a way, or temporal becoming in a way that is foreign to classical physics. You find such claim in Heisenberg. I put Abner-Chimony here in double brackets because, well, there is some tendency in his writings, but I would not pin down such thing to him. And, well, the problem with that is that you don't have any free-floating possibilities in the world. In the first place, you have to, in German you would say, Farbe bekennen. In the first place, you have to say what your ontology is, what there is in the world, and on that, what there is that may fix or determine certain possibilities or potentialities or whatever, but there can't be just a world of potentialities and then somehow what there actually is arises out of that, and even worse if combined with such a view. So all this goes to the wastebasket for the time being, and I will have some comments or arguments or hinted arguments why this cannot go through as metaphysics following from quantum physics, although there may be something right in these things, but not as put down here. Move on to something else. Here's what David Albert said earlier this afternoon, and I'm sorry, I should have changed my slide when I saw that Tim had this also in his way. So very brief, David Albert's claim is that quantum mechanical realism in whatever form it takes requires us to accept wave functions as physical objects in and of themselves, so that we are committed to the space in which these wave functions live in, namely configuration space, and that whatever impression we have to the contrary is somehow flatly illusory. Now, this is serious metaphysics. And why is it serious metaphysics? Well, one reason is that it applies to any formulation of quantum theory, whereas all the other claims I had on the list before apply only if you put in or if you make a certain controversial move, to say the least, without giving an argument for that move. Now, this is serious because any known formalism of quantum theory will involve a fundamental law that is about the temporal development of the wave function, or that is about the wave function if the wave function should be stationary. So on this basis, you may claim or suggest the claim that the ontological commitment when we interpret the theory is to a universal wave function as a field in high-dimensional space, and the law then concerns the development of that one object. Nonetheless, I would take issue now with the claim here that the realism in whatever particular form it takes commits us to that, because as you can learn from philosophers such as Putnam, Hacking, or Cartwright, realism is not only theory realism, but scientific realism can, should, or involve, or may involve also a realism about experimental practice. And experimental practice, of course, is committed to measurement outcomes in the sense of there being some matter distributed somewhere in a three-dimensional space or a four-dimensional space-time, local Beebles, in the sense of John Bell and as explained by Tim Maudlin. And if you reject that commitment, what you can do, and what is perfectly consistent and I won't say reasonable, but reasonable in the sense it's a serious option to do so, then you need an account of the appearance of matter distributed in three-dimensional space-time. Why it appears to us that there are such things, and that account cannot be based on the formalism of quantum theory alone. It requires you going in the philosophy of mind, taking a particular stance about what minds are in the world, what perception is, how perception is related to the external world, externalism, internalism, the same about language and semantics. So it involves a whole metaphysical package in which the physics plays a role, but which cannot just be determined by the physics, which cannot just be that the simple, of course, I guess nearly everybody in this room is a realist. It cannot be that simply being a realist and having the formalism of quantum mechanics takes you down all that road. It requires putting a certain metaphysics in and getting a certain, possibly perfectly consistent, reasonable view out of it.
For clarification, can I ask, in the last slide, the first line just short-circuits that?
Pardon? Scientific realism is not only
short-circuits this other. Is that correct? Is that what you mean?
I mean what I say there. I'm a scientific realist. This involves not only that I'm a realist with respect to theories, but also with respect to the way in which theories are confirmed, etc. It involves.
And therefore, all these other problems don't arise?
Why? Why don't they arise? It just says then you can be an experiment. I'm not particularly a fan of hacking or Cartwright, I have to confess, but I think they are right insofar as they point out that when we are realists, we should also be realists with respect to experimental practice. And if we are realists with respect to experimental practice, then the slide goes on, you're a realist with respect to matter, something being here now. And if you are not, that's why, sorry, the only thing I know to manipulate on such a computer is the color. So here the argument changes. If you are not, as David Albert is not, or I read him as not being, then you have to do something, which may be doable or not, that's not the point here. But then what you then have to do something cannot be based on the formalism of quantum theory alone. All I want to say is to you, the physicists need the philosophy. If you want to say something about the world, the formalism of a physical theory alone won't give it. You need the philosophy, you need the metaphysics, you have to put it in, and it does not follow just from the formalism. And this is an example, I have more examples of that claim. So you can say, you can subscribe to a commitment to the wave function, etc., but then you have to put in some metaphysics, some philosophy over and above the simple fact of taking the formalism of a particular physical theory seriously, so that you get to a dividing line, to a move that you have a fundamental decision that you have to.
What do you mean? Can you say, what do you mean by the formalism of the theory?
What you read in a textbook or what you are taught in a physics course.
No, it's just essential here whether you mean by the formalism purely the mathematics or something that transcends. I
mean what you're told when you sit as a student in Lausanne. It's the third-year students when they sit in the course, and there is some physics teacher, some physics professor, and that professor says that he teaches them quantum physics and he gives them a certain script, which I looked also, etc. And that's what I mean by there are certain formulas in there, there are certain rules, and there are certain things that are told about it. There are certain laws, equations put down, such as the Schrödinger equation. There are certain recipes given how to apply these equations, how to solve the problems. That's the textbook account of quantum mechanics. Okay. So the dividing line in trying to cook out an interpretation of that formalism is whether or not you acknowledge physical space with matter distributed or not do it. And when you do it, then you have something like a primitive ontology, local Beebels. So where you get this is that these things come in packages. And each of these packages involves both physics and metaphysics. So, and there are exactly two packages. There are not 3 or 4 or 5, not only one, exactly two. The one is that you subscribe to an ontological commitment to the wave function, and this then commits you to taking a particular stance in the philosophy of mind, perception, and language to save the phenomena, or you start from, and this was clear, I think, in Tim's talk about John Bell, you take for granted an ontological commitment to matter and physical space and a law then for the temporal development of that matter. But this you then have to put in as the referent of the formalism of quantum theory. Then the formalism cannot be or cannot just be about the wave functions, but it is about something else, namely matter distributed in physical space. And what you then get is an ontology as in classical physics, three-dimensional space, four-dimensional space-time, with some matter distributed in it, be it particles or fields or whatever. That's not the point here now. That is an ontology as in classical physics in the sense that you have some matter distributed in ordinary space, and the specific quantum aspect then only is the law for the temporal development of that matter. So the law will be non-classical. As in Bohmian mechanics, you have the Schrödinger equation, you have a law, the guiding equation, referring to particles, classical entities. But these classical entities are subject to a non-classical law. You have in the GRW theory a non-classical law, the GRW equation, and you have a distribution of matter and physical space put in by hand, so to speak, as the referent of that equation, of that law, of what you're talking about, be it density stuff, be it flashes. And the rational, the reason to have that is to interpret the quantum formalism as referring to distribution of matter and space, to save experimental realism, common sense realism to do. And then the point is you have to put in this, the formalism in itself does not give you as its referent or as that what it represents, the distribution of matter in ordinary space. So let's draw a few conclusions from this situation or debate. So if you think that three-dimensional space or four-dimensional space-time with matter distributed in it exists, if that is your starting point, then you don't have to make, or then it would be unreasonable or nonsense to make a fuss about your ontology. Then your ontology, your basic ontology, is the same as the ontology of classical physics. And if you want to have a non-classical ontology, which you can have and which may be reasonably, etc., then that ontology does not have in it a commitment to a three-dimensional space or four-dimensional space-time with matter put in it. And every other position that confuses these things, that mix them up and puts in ordinary space things which don't have a localization in there, etc., just is confused. You either go on the side, you either go with John Bell and Tim Maudlin and say this three-dimensional space, at least for the region where we live in the universe, etc., exists with matter distributed in it, but then you have a classical ontology, then you have bought into a classical ontology. Or if you don't want that, then you have to go with David Albert for an ontology of a wave function and configuration space. Then you have to go down all that way. You can't stop in the middle. So, and either of these ways of doing your ontology or metaphysics of quantum physics is sufficient. So it would be extravagant, to say the least, more than necessary, more than needed for anything, to have an ontology in which you have a wave function in a configuration space existing as part of commitment of your theory and matter distributed in three-dimensional space. Because if you are committed to matter in space, then the only job the wave function can do, or the only job everything else can do, as the Maudlin said before, is to be part of the law for the temporal development of the distribution of matter in three-dimensional space. And then, if it is... Pardon?
It's not so insistent at all. That was just a possibility. That wasn't what Tim was saying. But there's Tim. Okay, that's what Detlef asked to me, tell you things so that everybody will contradict me. But this is, that's why there is an hour to discuss all
these talks. I just say, I don't say you can do it, I can do a theory on which there are pink elephants in this room, or ghosts or whatever. I can't refute it, it's just that I don't need them. I would do a theory, I mean, you don't have any motivation to do a theory on which you have, well, you can't solve this controversy and this problem as the Greeks solved the problem whenever there was a new god, etc. You build up another temple. You do with either one of these packages. There's no point in mixing them up. So what I want to take you a little journey into philosophy now is to look a little more into this matter of laws. The claim then is that if you go, suppose you go for a commitment to matter and space, and suppose I'm right to say then to have what else you want to have in your ontology can only be motivated by having something that fixes the temporal development of what you have in your ontology, namely the matter distributed in the space, then that is a law. And the next claim then is that any one of the philosophical stances with respect to laws is applicable, and this again will teach us something about how we can interpret or how we should interpret. Philosophers will sometimes tend to make normative claims and then get fired at by everyone else, but I'm happy to get fired at. So here is one of the greatest philosophers of the 20th century, David Lewis, who was inspired by another David Hume, who lived 200 years ago before, and who is a great philosopher because he can tell you what the world is like in 2 or 3 sentences. So he does not lead like Hegel or so at 3 volumes in which there are no intelligible sentences, just 3 sentences. So Humean metaphysics is the doctrine that all that there is to the world is a vast mosaic of local matters of particular fact, just one little thing and then another. We have a geometry, a system of external relations of spatial-temporal distance between points, and at those points we have local qualities. For short, we have an arrangement of qualities in space, in 3-dimensional space, and that is all. And he wants to be, David Lewis wants to be that to be all, because he does not want anything like necessary connections. So the allusion to David Hume is that Hume rejected the idea of there being any necessary connections or anything, put it in more general term, anything like objective modality out in the world, something more than contingent matters of fact. And he wants, and you chase out unnecessary connections, any modal things out of your ontology by just having this Humean mosaic of local matters of fact, local qualities occurring at a space-time point. If and only if you can hold fixed each of these local qualities and vary all the other ones. That's to say, whatever there is at the space-time point does not impose any constraints at all of what will happen in the future, of what there is in its neighborhood. And Tim Maudlin, in a very good and famous book about the metaphysics which there is within, or supposed to be, within physics, takes issue with this claim, claiming that quantum entanglement, the non-separability of the quantum state, refutes Humean metaphysics, so that out of quantum physics we get a commitment to a certain view of laws and to a certain stance with respect to modality, namely that there is objective modality in the world. And again, this is a serious claim. Why? Because we have Bell's theorem, and as I said before, Bell's theorem is something, if you're not, you don't have to be realist about non-relativistic quantum mechanics, because if you're realist about relativity as well, etc., you want some other story, and you may want the story of gravitation, etc. But whatever that story may be like, Bell's theorem will pose a constraint on it. Will pose a constraint in the sense that any theory that is to be empirically adequate has to recognize correlations between space-like separated events, and these correlations cannot be accounted for by a common cause in the intersection of the past light currents. So this is it's a very completely reasonable, well-motivated claim to say that this commits us to recognizing relations of quantum entanglement over and above what is admitted in what David Lewis describes as Humean metaphysics, namely external geometrical relations between points and stuff located at these points. Now again, there's a but from my talk. This does not simply follow from quantum physics. Why not? Because the entanglement is a feature of the wave function and configuration space, and there are no direct conclusions from entangled wave functions to what there is in space-time possible. And here's a quotation from John Bell from the paper The Theory of Local Beebles, the only quotation from Bell I have, and I don't want to enter into Bell exegesis, so this is not necessarily, or not, probably not, this is a position that Bell contemplates, but you should not read him as being committed or subscribing to it. Here's what he says. One of the apparent non-localities of quantum mechanics is the instantaneous over all space collapse of the wave function on measurement. But this does not bother us if we do not grant Beeble status to the wave function. We can regard it simply as a convenient, it's a convenient but inessential mathematical device for formulating correlations between experimental procedures and experimental results, that is, between one set of Beebles and another. Now, this, what Bell says here, and it's not what he says in other places, very well fits what that guy, David Lewis, says here. So if you put that citation of John Bell together with that citation of David Lewis, you get, as a perfectly possible, reasonable, coherent position, a quantum Humeanism. You have only your local matters of particular fact, that is the distribution of matter in space-time, be it particles, be it some mass density, be it flashes or whatever that may be, and the quantum state does not exist. The wave function simply is part and parcel of the best description, of the most economical description of the distribution of matter. The Humean-Lewis view of laws is that laws of nature just are means of economical bookkeeping. And instead of simply saying for each share in this room whether it's occupied by a person, I can give a more general description which will have more or less the same informational content, but which will be simpler. And the description which combines in the best way simplicity and empirical content is, or gets the status, or gets called a law. So the wave function, if it is part of a law, is part of a description of what there is in space-time, and that description, to be economical, to be as simple as possible, correlates local Beebles independently of their spatial distance, but on this view it has no ontological significance. There are no relations of entanglement instantiated in space-time. This commits you then to saying that there is nothing that drives, that fixes, that determines the temporal development of matter and space. There just happen to be flashes, there just happen to be particles moving on certain trajectories, there just happens to be a certain density of stuff, but there is nothing that fixes, that governs, that determines its temporal behavior. So you don't get any explanations in fundamental physics. You just get the matter, which is the primitive stuff. You just get, as some chairs in this room are occupied and others are not, so you just get some space-time points are occupied and others are not, but what occupies these space-time points? Just the stuff. It does not have any properties. And this, again, is a possible metaphysical package. So again, the same story again. You always get, you have to put the metaphysics in it, then you can make sense of the physics, and the physics will shape, will influence your metaphysics, but not the physics, qua physics as such, but depending on your metaphysical premises. So you have, again, a package which gives you Humeanism and a primitive stuff distributed in space-time without properties, nothing fixing its temporal evolution, no explanation, or you get objective modality, namely the primitive stuff and something else, and that something else can now be a law instantiated in space-time, on Tim's views of law, that fixes the temporal development of the stuff, a law anchored in a property of matter in space-time, which would then be a disposition, and which would, in this view, have to be a holistic property that covers all of matter, and which would be modal because it fixes what is possible and what is not possible for the temporal development of the matter. Then you get something else. But the view again is you have two packages there which involve both physics and metaphysics in an inseparable way, and you have to evaluate these packages. So we get to a few conclusions. The first conclusion is that you should be careful in the way you talk about properties. Properties are not predicates in language. Properties, if they exist, they are something that exists in the world. And you need properties in physics only if you endorse a metaphysics which says that there is something that fixes the temporal development of the distribution of the primitive stuff. Otherwise, forget about properties. Otherwise, just go for a parsimonious unionism that just have stuff. So if you want properties in physics, then they better be ipso modal. Otherwise, it's Schall and Rauch, talk without sense. So, and you see it is Schall and Rauch, you see that it is nonsense to associate operators with properties. It does not make any sense at all. There will be a discussion session. So the second conclusion is that to worry whether physical equations are deterministic or indeterministic casts no ontological eyes, so to speak. The issue is whether or not you're committed to something in space-time that fixes the temporal development of the distribution of your stuff, but that is a metaphysical commitment that has nothing to do with the equations for in a certain physical theory being deterministic or stochastic. So you can have unionism and deterministic laws without any problem, but still there would not be anything in your ontology, there would not be anything in the world that determines, that fixes, that influences the temporal development of matter. And you can have dispositionalism, or the view that a law fact or law is instantiated in the world, and stochastic, the laws of that world being stochastic, but still you would have something that fixes the temporal development of the matter, propensities or the law qua being instantiated, etc. So all the fuss made about whether laws are deterministic or stochastic in physics is pointless as long as you do not take the metaphysics of laws into account and take a certain position in the metaphysics of laws. So that in a general conclusion, to cut this short, the interpretation of a physical theory means spelling out an ontology for the theory, and that ontology in no case is deducible from the formalism. So the idea of a naturalized metaphysics in that methodological sense is an illusion. What you need and what you should do, and what physicists in the great days of Newton and those earlier centuries did, is natural philosophy, which involves both physics and metaphysics in a seamless manner. The matter, you have to put in certain metaphysical commitments, then you can make sense of the physics, and the physics will in turn have repercussions, shape your metaphysical commitment. So if you have a metaphysical commitment to there being properties in the sense of dispositions, then quantum physics tells you that they have to be holistic or non-local or things like that, that they have to be non-local beables. But if you don't have that metaphysical commitment, you don't need this. And the aim, of course, is to achieve an overall coherent and convincing conception, which again will involve evaluating both physical and metaphysical claims, and the only measure in the end you have is whether the package as a whole makes sense, is convincing. Thank you.